Hey everybody, lesson 22 is all about finding the derivatives of natural log functions. We started this briefly in class sometime last week, but I'm just going to go over all of it again. So let's get started. Here we have the rule that tells us how to take the derivative of a natural log function, and it is important to note that u is everything that is on the inside of the natural log. Now, this u is not to be confused with the u that we use in u substitution. This u is specific to us finding the derivative of a natural log function. So in example 1, we have y is equal to natural log of 3 divided by x. U is everything that's on the inside of natural log, which is 3 divided by x. I'm going to rewrite that as 3x to the negative 1. I haven't done anything. I just rewrote it to make it a little bit easier for us to find u prime. So I'm going to take the derivative of u, bring down my exponent of negative 1 to get negative 3, decrease the exponent by 1 to now get negative 2. So u prime is negative 3 over x squared. Now the rule tells us that y prime is equal to u prime divided by u. To find the derivative of a natural log function, you take the derivative of whatever is on the inside and you divide it by whatever was originally on the inside. So our u prime is negative 3 over x squared. So we will take that and we will divide that by our u, which is 3 over x. We're dividing fractions. I will keep the one on the top the same, and I will multiply by the reciprocal of the one on the bottom. Our 3's will cancel. We will still have a negative, and one of the x's will cancel. So we are left with a negative 1 over x. Looking at example 2, we are taking the derivative of h of t, and h of t is a product, so we will need to use the product rule in order to take this derivative. I'm going to identify our f and our g. Our f is going to be t, the first factor there, and our g is going to be natural log of t all squared. Notice that the squared is applied to the natural log and the squared is not being applied to the t on the inside of natural log. So in other words, I'm saying it is not this. It is natural log all being squared. Let's find our f prime and our g prime. The derivative of t is just 1. For g prime, we're going to have to use the chain rule. I'm going to bring the exponent of 2 down in front of the natural log. The new exponent, I'm missing a t. The new exponent on the natural log is just a 1, but we don't have to write that. But the chain rule says that we have to multiply by the derivative of whatever is on the inside, and the derivative of natural log t is 1 over t. Because when we're finding the derivative of natural log t, remember we're doing u prime over u. So just really quickly, u in this case is t, and u prime is 1. I'm going to rewrite our g prime just so it looks a little bit better. This is really 2 natural log t all divided by t. And now we're ready to look at what h prime of t is, which will be f prime g plus g prime f. This is us using the product rule. F prime is 1. G is natural log of t all squared. G prime is 2 natural log t divided by t, and f is t. We can cancel these t's down here, and we are left with natural log of t all squared plus 2 natural log t as our final answer for h prime. In example 3, we will be using the quotient rule because we have a quotient that we're taking the derivative of. Our f is what's in the numerator. It is natural log of x. Our g is what's in the denominator. It is 1 plus natural log of x. F prime is 1 over x because the derivative of natural log is u prime over u, and in this case, u is x because u is what's inside natural log and u prime is 1. The derivative of g will be the same thing because the derivative of 1 is just 0 and the derivative of natural log x is 1 over x. So now let's apply the quotient rule to find y prime, which is f prime g minus g prime f all over g squared. So we're going to be plugging in now. F prime is 1 over x. and that is multiplied by g, which is 1 plus ln x, and we do need to put that in parentheses because that's all multiplied by g. Then we are subtracting g prime multiplied by f, so that's 1 over x multiplied by natural log of x, and this is all divided by g squared, which is 1 plus natural log of x, all in parentheses, squared. There's not really a lot that we could do here to simplify this. Well, there is a little bit that we can do here to simplify this. Let's distribute in the numerator. So in the numerator, we have 1 over x times 1 plus 1 over x times natural log x minus 1 over x times natural log x. And then all of this is still divided by 1 plus ln x squared. And the reason I distributed in the numerator is because now this term and this term can cancel. And we are just left with 1 over x divided by 1 plus natural log of x all squared. And then because we are dividing fractions here, I will again multiply by the reciprocal. Think of that as 1. And so this is 1 over x multiplied by 1 over 1 plus natural log of x all squared, which just comes down to the x and the 1 plus natural log x that's squared being in the denominator. And that's our final answer there. Example 4, where we'll be finding the derivative of natural log of secant plus tangent. Let's start off by identifying u. Notice that in example 3, only reason we use the quotient rule is because we had a quotient that involved natural logs. In example 2, only reason we use the product rule is because we had a product that was involving our natural logs. Example 4 does not have neither a product nor a quotient, so I won't have to use the product rule and I won't have to use the quotient rule. I will just be using this rule along with some trig definition, some trig derivative rules. So u is everything that's on the inside of natural log, which is secant theta plus tangent theta. And then we'll take u prime. We'll take it term by term. The derivative of secant is secant tangent, and the derivative of tangent is secant squared. So we have this. And now we will be doing u prime divided by u to give us g prime of theta. So we are taking u prime and we are going to divide that by u. U prime is secant theta tangent theta plus secant squared theta. We are dividing that by u, which is secant theta plus tan theta. And I hope you don't think anything here can cancel, because nothing here can cancel. And I will just leave this like that. Example 5, we will still be dealing with the derivatives of natural log functions, but now we're going to look at some applications of that. We have seen how to use the first derivative to find absolute extrema on an interval. So we're going to be doing that in example 5. Quick recap of how we do this. We need to find our critical values, and then we need to make a table with our critical values and our endpoints all plugged into the original function to see which one gives us the largest value and which one gives us the smallest value. Let's start off finding g prime of x. To find g prime of x, we're going to need to use the derivative rule for natural log. In this case, u is cosine x, because that is what's on the inside of natural log. And the derivative of cosine is negative sine x, so our u prime is negative sine x. So we have u and we have u prime, so g prime of x, the natural log derivative rule, is u prime over u. So that is negative sine x over cosine x, which it does equal a negative tangent x, but I don't think that's going to be very helpful for us to do right now, because remember, what we're trying to do is we're trying to find critical values, and critical values will happen where the derivative is equal to 0 or where the derivative does not exist. Now, this derivative will equal 0 when its numerator is equal to 0, and the negative doesn't really matter. We can just really say when sine x is equal to 0. The derivative will not exist when its denominator is equal to 0, so when cosine x is equal to 0. And keep in mind that we are working on a specific interval in here. This interval from negative pi over 4 to pi over 3 looks something like this. There's my x-axis, there's my y-axis. Negative pi over 4 is about right here. And pi over 3 is about right there. So we're only looking in this interval there. So where does sine x equal 0 in this interval? Sine is the y-coordinate. That's going to happen at 0. And where would cosine x equal 0? Cosine x equal to 0 is not going to happen on this interval because cosine is only equal to 0 at the top of the y-axis and the bottom of the y-axis. But we're only working between negative pi over 4 and a positive pi over 3. So cosine x being equal to 0 never happens on the interval negative pi over 4 to a positive pi over 3. So we only have one critical value, and it is x equal to 0. So now I am going to make a table where I'm going to take some x values and I'm plugging them into the original function g of x. And the x values that we are plugging in are our critical value of 0, our left endpoint of the interval of negative pi over 4, and our right endpoint of the interval at positive pi over 3. We're going to plug these into the function and see what we get out. I'm going to grab my calculator and plug these in. Make sure that your calculator is in radian mode. And do not forget to put the y equals what? And do not forget to put the natural log of cosine x in your y equals. Okay. When I plug in 0, I get out 0. When I plug in negative pi over 4, I get out about negative 0.347. I'm rounding that. And when I plug in pi over 3, I get out about negative 0.6931. I'm going to erase this so we can write our answer. The largest value gives us our absolute max on the interval. The smallest value gives us our absolute min on the interval. So between negative pi over 4 and pi over 3, the largest value that came out is 0. So we have an absolute max of 0 at x is equal to 0. That is in that interval. And then we have an absolute min of negative 0.6931 at x is equal to pi over 3. And you can look at the graph and confirm that. Is when you're looking at the graph, make sure that you are paying attention to the interval that you are actually working on there. Example 6, we're going to find intervals of increasing and decreasing for this function h of x. This is another example of us using the applications of derivatives. In order to find intervals of increasing and decreasing, we are using the first derivative test. We need to find critical values, make a number line, or test intervals, choose numbers in the test intervals, and see whether the derivative comes out positive for the function to be increasing on that interval, or if the derivative comes out negative for the function to be decreasing on that interval. So the first thing I'm going to do is I'm going to start with h prime of x. I'm going to take the derivative term by term. The derivative of x is 1, and the derivative of natural log x is 1 over x. We are now going to find critical values. We're going to see where the derivative is equal to 0 and where the derivative does not exist. Well, our derivative is not going to exist when x is equal to 0 because that's what's in the denominator right there. So I already know that x equal to 0 is going to be one of our critical values. And I'll say something else about that in a second. Let's see where the derivative is equal to 0. I'm going to set 1 minus 1 over x equal to 0. Add 1 over x to both sides. I get 1 is equal to 1 over x. And then we can multiply both sides by x to see that x is equal to 1. So we have 2-ish critical values. I say ish critical values because what you learned, I don't like it when I say this, but what you learned back in 171 is that the domain of the natural log function is 0 to infinity, where the 0 is not included. You cannot plug anything into a natural log function if it is negative. If you try to hit natural log of a negative number on your calculator, you're going to get an error. So, and even more so here, think about this example here. This natural log of cosine x. On the interval that we were on, remember the little drawing I had? Negative pi over 4 to positive pi over 3. On this interval here, cosine is positive on that interval because all of those x values are positive on that interval, right? So you cannot plug things into natural log that are negative. or 0. You cannot plug 0 into natural log either. So if 0 is not in the domain of our function, it's not going to count as a critical value either. It is not in the domain of h of x. So we don't have to consider that as a critical value. We only have one critical value here, and that is the critical value of 1. So I am going to make an interval, a number line rather, and on that number line I am going to put 1 on it. I'm going to test a number that is smaller than 1. I'm going to test a number that's larger than 1. Now when we test a number that is smaller than 1, in fact, it's probably a better idea for you to start your number line at 0, because it doesn't make sense for us to look at anything smaller than 0 or 0 by itself. I'll choose 1/2 right here, and I'll choose 2 right here. And this is a number line for h prime of x. So this is going into this derivative up here. When we plug in 1/2, we're going to get out a negative number. And when we plug in 2, we're going to get out a positive number. So that tells us that this function is increasing, not from negative infinity to 1, but from, oh wait, ignore that right now, increasing from 1 to infinity, because that is positive. This is increasing from 1 to infinity. And the function is decreasing, where we got the minus sign, where we plugged in the test value of 1/2, decreasing not from negative infinity to 1, but from 0 to 1, with a parenthesis on 0. And you can look at the graph of x minus natural log x. I'm punching that into my calculator right now to confirm that. Yep, it's decreasing between 0 and 1, and then starts increasing from 1 to infinity. Now, example 7 is another example that I think we looked at together in class. And the idea behind this is, if we were going to take the derivative of this, this would look very, very, very messy. Don't write this down, but we would have that u is everything on the inside of the natural log function. And then u prime, we would need to use the quotient rule to take that derivative. We'd also end up using the chain rule and the power rule and the product rule. We would have to use all of those rules to take u prime. The derivative of u would look very, very, very messy. There should be a p, y'all. There should be a p. That 3x to the 4th, make that a 3p to the 4th. That should be a p. Anyways, that derivative would look very messy. And so it's an easier way to take this derivative if we remember our properties of logarithms, which are these properties here. These are properties that come back from 171. So first thing I'm going to do is I am going to apply those properties to decompose that logarithm. And let me just pull a quick little screenshot over to show you all how I am using the properties as I use them. I wonder if I can get it to just paste. Of course not. Let's stick that right there. Okay. So let's start breaking this down. First, we're going to start breaking this down using the quotient rule, because there's a quotient on the inside of the natural log. The quotient, and so mind you, I'm not taking any derivatives yet. I'm just using these properties of logarithms. The quotient rule tells us that we will have natural log of whatever is in the numerator minus natural log of whatever is in the denominator. So we have that. On this first logarithm here, we have a product on the inside of the logarithm, with p being multiplied by that 1 minus p squared cubed. So I'm now going to use the product rule to separate that into two separate logarithms. I'm going to have natural log of p, that first factor, added to natural log of 1 minus p squared all cubed, that second factor. And that second logarithm, I'm not going to do anything to it yet except for rewrite it. Instead of using the 4th root, I'm going to write it as the 1/4 power. The first logarithm I'll just leave alone for now. That's natural log p. The second logarithm, we can use the power rule to bring the exponent of 3 down in front of the logarithm and leave us with 3 natural log of 1 minus p squared. And then I'm also going to use the power rule to bring this exponent of 1/4 down in front of this logarithm to give us natural log of 3p to the 4th minus 5. Now that I have this expanded out, it'll be a lot easier for us to go in and take the derivative of these terms versus us taking the derivative of the original function. So now I'm actually going to start writing h prime of p. So when I go in and look at the first term to take the derivative, u is just p and u prime is 1. So the derivative of natural log p is just 1 over p. Going to take the derivative of the second term, I'll keep the constant of 3 that's out in front. Here, u is 1 minus p squared, everything on the inside of natural log, and u prime is a negative 2p. So this derivative is a negative 2p over 1 minus p squared. Remember, it is u prime over u. For the last logarithm, I'll go ahead and bring down the coefficient of 1/4. Here, u is everything on the inside of natural log, which is 3p to the 4th minus 5, and the derivative of that is a 12p cubed. And so this derivative here is 12p cubed divided by 3p to the 4th minus 5. And I'll just leave that like that. That is our derivative. And so notice how it is much easier for us to take the derivative once we have applied rules of logarithms to both sides, which is something that we will be looking at further now as we look at logarithmic differentiation. Instead of just going through these steps, let's just look at example 8 and then we'll go through the steps as we go through it. So example 8, use logarithmic differentiation to find the derivative of this function. Mind you, if you were not going to use logarithmic differentiation to find the derivative of this function, you would need to use the product rule a couple of times because you'd break it up probably like that. And then when you had to use this, find this derivative, you'd have to be using the product rule again with the t and the t plus 1. So that could get very messy. And it's typically for problems where the derivative the process to find the derivative could be very messy, that logarithmic differentiation makes it a lot simpler. Step 1 of logarithmic differentiation tells us to apply natural log to both sides of the equation. And that doesn't change anything because we're doing it to both sides. So we have natural log y is equal to natural log of t times t plus 1 times 2 minus t. Step 2 tells us to simplify with logarithmic properties. So there's nothing we can simplify on the left side. That's just going to stay natural log y. But on the right side, I can simplify using the product rule because I have all of these 3 things on the inside of this logarithm that are being multiplied together. And so I'm going to separate them and add 3 separate logarithms. By the way, y'all, keep in mind, the product rule, I know it only has 2 things right there. But even if it had 3 things like what we had, it's the same thing. It doesn't matter how many things are on the inside of the logarithm. If they're all being multiplied together, you can break them up into separate logarithms and just add them. So we have natural log t plus natural log of t plus 1 plus natural log of 2 minus t. That's us applying the product rule to break up that product on the inside of that logarithm into separate logarithms. Step 3 of the process to differentiate using logarithms is to take the derivative of both sides of the equation. So I'm going to go ahead and take the derivative of both sides. The derivative of natural log y is y prime over y. Remember, it is u prime over u. The derivative of natural log t is 1 over t. The derivative of natural log of t plus 1 is 1 over t plus 1. The derivative of natural log of 2 minus t is a negative 1 over 2 minus t, because in this case here, u is 2 minus t, and so u prime is a negative 1. So I have a minus sign here, 1 over 2 minus t. Step 4 says to simplify and solve for the derivative. So for step 4, we need to solve for the derivative. The derivative is just what's in the numerator here. So to solve for that, I'm going to be going through and multiplying both sides of this equation by y so that I can cancel out the y that's in the denominator on the left-hand side. So I have y prime is equal to 1 over t plus 1 over t plus 1 minus 1 over 2 minus t, and that's all multiplied by y. And we know exactly what y is. Y is this. So this y is t times t plus 1 times 2 minus t. And now I will simplify this. I was trying to think if I wanted to do it or not, but let's just go ahead and do it. So all three of these factors need to get distributed to all three of those terms. So when I distribute to the first term, the 1 over t, the t's will cancel and just leave me with t plus 1 multiplied with 2 minus t. When we distribute to the second term, the t plus 1s will cancel and just leave us with t multiplied by 2 minus t. And when we distribute to the third term, the 2 minus t's will cancel and leave us with a negative t multiplied by t plus 1. And that is our final answer for our derivative. Example 9, our last example in this video, we will be using logarithmic differentiation again. We're going to start off taking natural log of both sides. So we have natural log of y is equal to natural log of theta plus 5 divided by theta cosine theta. I'm going to go ahead and use properties of logarithms to simplify the right-hand side of this. There's a quotient on the inside of that natural log, so I'm starting with the quotient rule, which tells me to take natural log of what's in the numerator and subtract natural log of what's in the denominator. I'm going to continue to simplify the right-hand side of this. There is no rule to simplify addition on the inside of a natural log. And let's make sure we're clear on that. The product rule is called the product rule because you need a product on the inside of the log. The quotient rule is called the quotient rule because you need a quotient on the inside of the log. And the power rule is called the power rule because you need a power on the inside of the log. There is no sum rule that tells you what to do for this, and there is no difference rule that tells you what to do for this. Those cannot be simplified. Continuing. We do have a product on the inside of this logarithm. Please make sure you are using parentheses right here. The product rule tells you that you can separate these two by adding natural log of the two separate factors. And the reason I say please make sure that you're using parentheses is because you will need to distribute that negative to both of those terms there. One way to remember that is anything that showed up in the denominator should be inside of a negative logarithm. And so I mean both that theta and that cosine are showing up in the denominator, and they're both inside of negative logarithms. So we have used properties of logarithms to expand this out. Again, remember there is nothing we can do to that first log because we do not have a sum rule for logarithms. And so now we're going to start taking the derivative of both sides. The derivative of natural log y is y prime over y. That's just using the u prime over u rule. We're using the same rule here. U is theta plus 5. U prime is 1, so this derivative is 1 over theta plus 5. Using the same rule for the second one. U is theta. Derivative of theta is just 1. So this is 1 over theta. Same rule for the last one. U is cosine theta. The derivative of cosine theta is negative sine theta. So we have a negative sine theta over cosine theta. Let's just clean this last term up a bit. We have y prime over y is equal to 1 over theta plus 5 minus 1 over theta. That last term, I'm just going to write it as a positive tangent theta. Positive because we have these two negatives right there coming together to give us a positive, and sine over cosine is tangent. Last thing we have to do is we have to solve for y. So I'm going to, y prime, excuse me. We have to solve for y prime. So I'm multiplying both sides of this equation by y. So I have that y prime is everything we have in parentheses here. And y, I'm going to be replacing with that, which is theta plus 5 over theta cosine theta. And I'm just going to leave that like that. You could distribute that in, but I'm just going to leave it like this. And there's our answer.